Good afternoon and welcome to our 5th webinar of 2021. We want to start by saying thank you to all of you for being part of this and previous webinars throughout 2021. We are already working on the list of topics for 2022 webinar series. If you would like to share specific topics for us to go over them, please share it with us via email at support@I-Gard.com. If you want to watch the recordings of previous webinars, please go to www.I-Gard.com, click on Technical Library menu, then click on Videos and Webinars, and you will get direct access to these resources. You can also visit I-Gard's YouTube channel, and all the webinars recordings are posted there as well. If you have any question during the session, please type them in using the Q&A section. It is located in the toolbar at the right side of your screen. Sergio will answer as many questions as possible at the end of the presentation. Today's webinar is entitled Hybrid Grounding of Generators. It will be presented by Sergio Panetta. Sergio is the Vice President of Engineering at I-Gard.com. At I-Gard Corporation. He's a graduate of McMaster University with over 3 decades on electrical engineering experience in switchgear design, commissioning, and troubleshooting of power system protection and power system grounding. Sergio is a senior member of the IEEE, member of the IET, and he has been awarded consulting engineering status with the PEO professional body. Sergio is the author of numerous industry editorials, application white papers, and he is actively participating in industry safety and standard committees. Sergio is the author and owner of several patents related to electrical safety. Please join us in welcoming Sergio Panetta.
Thank you, Miriam. Can you hear me?
Yes, I can hear you.
Okay, great. I just wanted to make sure. So our topic today is going to be hybrid grounding of generators. But hybrid grounding is really hybrid high resistance grounding. So why is it called hybrid high resistance grounding? It's not really a high resistance grounding system. A hybrid high resistance grounding system resembles a low resistance grounding system for the most part, but protects medium voltage bus connected generators when there's an internal fault in the generator. So it switches over to a high resistance grounding system, allowing the generators to coast down and minimizing the damage. And I'll go through what the damage is. And this all started because there was some catastrophic failures in the United States, specifically the Pacific Northwest, where they've had some generators fail drastically under a stator fault winding, and so the hybrid high resistance grounding system was developed for that. So we're going to take a look. If you have a through fault, let's say for example you have 3 sources in this particular example. You have the generator, 2 generators, and engineers like to duplicate things. So if you have one 400 amp low resistance grounding system and you put in another generator, chances are it's going to be a 400 amp 10-second resistor. And the utility is going to be a 400 amp 10-second resistor. So if you have a through fault, and a through fault is going to be a fault somewhere in the facility, you're going to have, if all 3 sources are operational, then you're going to have 1200 amps of available fault current because all 3 sources are in parallel. And we'll talk more about this later. The breaker closest to the fault will trip. and both the Canadian Electrical Code and the National Electrical Code state that if you have a ground fault on a source which is greater than 150 volts to ground and greater than 1,000 amps, you must have ground fault protection. So you have to trip right away. But hybrid high resistance grounding was developed if you have a fault internally to the stator fault winding. So you can see a fault right there. We still have the 3 parallel sources when you have a ground fault inside the stator fault winding. So there are 3 sources. You open up the breaker because the differential protection is going to pick up that ground fault specifically on medium voltage bus connected generators and isolate that fault within 100 milliseconds. 1 cycle to detect the fault, 5 cycles for the breaker to open if you have a 5-cycle breaker. What that means, though, is the only thing you've done is you've removed this source and this source. You still have an internal source. So the contribution of the fault current due to this resistor and this resistor of 800 amps is 2,263 watt-seconds of damage in that fault inside the stator fault winding. If you had 4 generators or 4 sources at 400 amps, you'd have 1,600 amps. Or if each generator or if each source had an 800 amp ground resistor, you would have 6,400 watt-seconds of damage. And you could see here that that fault is going to stop contributing to the stator fault winding after 100 milliseconds or 6 cycles. Again, if you had more sources, 4 sources, 2 additional sources at 400 amps, you're going to be at 6,400 watt-seconds of damage. And the formula for calculating this is the energy is the integral of I raised to the K dt. Now we're going to take a look at what we do as protection engineers. So you still have the same stator fault winding. You open up the breaker in 100 milliseconds. But what we haven't shown here is we haven't really cleared this fault. We did what we could as protection engineers, and we opened up the breaker, separating the load from the generator, but we haven't separated the fault, the ground fault, from the stator winding because it's still captured inside this area. So the damage that occurs to the stator fault winding after the breaker has opened is 5,333 watt-seconds of damage. And that's because just because we've opened up this breaker doesn't necessarily mean we've stopped generating power. That generator is going to continue producing power until it winds down. And you can see here that the maximum fault current occurs around the 3 or 4 second mark. So if it takes a long time to wind down, then it's going to increase that damage. And the formula for calculating the damage due to the internal resistor, or the resistor connected to the generator with the ground fault, is the integral of I times e to the minus t over tau raised to the power k dt. So what happens here is, everything happens together here. So you can see that everything combines. We have the contribution of the 2 sources here, and the contribution of the internal resistor, and the total damage increases to over 7,000 watt-seconds of heat. So why this is important is because alternator manufacturers basically produce curves of stator fault winding damage. This is one manufacturer, and you can see here that the maximum fault current that they can have in their stator winding before extensive damage occurs in 100 milliseconds is about just 80 amps of current. We're putting in 400 amps of current through that stator fault winding, and it's more than 0.1 seconds. Second manufacturer has a different type of curve, but it's a stator earth fault current. So you can see that for A, you have acceptable damage, and it's limited to 25 amps for 1 second and decays. Considerable damage if it's in this B curve, and that's up to just under 75 amps of current. So you can see that generators considerably cannot tolerate a lot of current during internal stator fault windings. And then you have extensive damage if you exceed the time or current in these particular curves. For this reason, IEEE has experienced or formulated a committee in early 2000, late 1990s, and they developed a hybrid high resistance grounding scheme. And this particular scheme is what's shown in C37.101 stator ground fault currents or generator ground fault current protection. So you can see here the differential protection detects the ground fault within this zone. And if you have a ground fault anywhere in this zone, you open up the main breaker, open up the vacuum contactor, which isolates the low resistance ground in the system and allows the generator to coast down with a high resistance ground in the system. So 10 amp, and it doesn't need to be rated continuously. It's a 10-second resistor. Okay. The fault should have occurred first, and then you open up the breakers, but in this particular case, it didn't happen that way. So if you had multiple generators and they all had the hybrid high resistance ground system connected to it, you could see that you will have a stator fault winding, and you're going to have 810 amps of available fault current due to this resistor, and 410 amps. So 810 amps. This results in a damage of 2305 watt seconds. When you open up, the differential detects that fault in 100 milliseconds, isolating the 400 amp 10-second resistor and allowing the generator to coast down with a 10 amp resistor in it. So you have 3 curves here because you have the resistor. This part over here is for the 10 amp. This one over here, the red one, is for the system due to the 820 amps, 810 amps. And this one here is the 400 amp 10-second resistor, which is isolated by the vacuum contactor that's basically connected to the neutral and isolates with the differential protection. So there's an additional damage that occurs due to the internal resistance. If you wanted to avoid that complexity, because basically if you have this type of system and you want to add another generator over here, you have to add another hybrid high resistance ground in the system. So a simpler method or alternative method of doing this is to use a Zig Zag transformer that's on the bus. The advantage of this system is that your fault current, irregardless of how many generators are connected to the system, is going to be 400 amps. So you could see that in this particular design, the multiple of generators caused a multiple of 400 amps of ground fault current, whereas in this particular system, it doesn't matter how many generators are connected, your maximum fault current is always going to be 400 amps for 10 seconds. And the only thing you need to ensure is that 400 amps is greater than or equal to the capacitive charging current of the system, and we're going to discuss that a little later. So if you have a stator fault winding in this particular scheme, your fault current is going to be 420 amps, resulting in 861 watt seconds of energy being dissipated in that stator fault winding. When the generator isolates, you could see that there's only a 10 amp resistor left in the circuit, so it limits the fault damage to 21 watt seconds, and your total is 882 watt seconds. So already you could see that it's going to be a better system in that you have less damage at the point of the fault. And this is why we use resistance grounding systems, to have less damage at the point of the fault. However, those resistors have to be low enough to limit the fault current. And here's the damage curve. You can see here that you have the fault current of the 820 amp, and then you can slightly see an additional 21 watt seconds of damage due to the 10 amp 10 second resistor. So there's two things that you have to consider when you're using a hybrid high resistance grounding system. If the utility is always going to be connected to the system, you could have a 400 amp 10 second connected to the transformer and then a 10 amp resistor connected to each generator. As long as you don't island, this will do. If you're islanding, then the issue is you will not have enough ground return current to overcome the capacitive charging current of your system. So this is why a zigzag transformer on the bus will do. Now you're able to use the utility or the generators or both. In the previous example, this one, when we had the 400 amp resistor here, you always had to have the utility connected to the system. So when people come to I-Gard and ask for a hybrid high resistance grounded system, we always ask for the methodology of the generators being online. If they're going to island, you have to have enough ground return current for that island condition. For example, like this, you would have to have a ground return path on the bus. So, and the reason why that's important is because we have to have enough current to measure the charging current or to overcome the charging current of the system. So we're going to try to calculate what the charging current is. And I've shown an example here of a unit connected generator. The difference between a bus connected generator and a unit connected generator is the unit connected generator is connected to the transformer, a step-up transformer, and then it's distributed here. With this particular system, all you have to do with the resistor here is overcome the charging current. If you had a bus connected generator like this one, you only need to size this resistor for this portion of the circuit to overcome the charging current in this area. Once this breaker is closed, the 400 amp 10 second resistor will have enough resistive current to overcome the charging current. So let's look at the generator setup and determine how much charging current we have in the system. And whether it's a unit connected generator or a medium voltage bus connected generator, if you replace this with a circuit breaker, you're looking at the same thing. So if we take a look at the 10 MVA generator at 13.8 kV out of the, I don't know if you guys remember the T&D, Westinghouse put out a T&D book. This came out of that chapter in the T&D book, as well as ABB probably put out another book that reduplicated that. So the voltage is going to be, terminal voltage is a multiplier of 1. The generator is 0.05 amps, well, microfarads per phase, according to this chart. The charging current due to the capacitive cabling is going to be, if we look at the cabling from the generator to the transformer, we're looking at 250 feet of 500 kc mil, and you have 3 in parallel. The capacitive coupling due to the cable is caused by 2 potentials. So you have 1 potential here, you have another ground plane over here, so you have basically an isolation between 2 potentials, so that's a capacitor. So the cable capacitance is 0.0929 microfarads per 1,000 feet per phase. So the total capacitance is 0.07 microfarads. Going through the formulation, we have 22,000 ohms per phase. Your current is 0.62. 3 times that is 1.86. So realistically, if you had a unit connected generator, you could put a 5 amp resistor in here, limit the fault current to 5 amps, and not worry about a hybrid high resistance grounded system. But if you have a medium voltage bus connected system, then you have to put in additional current, because once that breaker is closed, you're picking up the charging current of the rest of the system. So I always stress the delineation between a 5 kV system and a 5,000 volt system. 5 kV is not 5,000 volts. And if we look at NFPA 70E and Z462, specifically Annex O 2.3, it basically says that high resistance grounding, a great majority of faults are going to be single phase to ground faults. And if you limit the fault current at 5 kV and below, there is insufficient energy to propagate to a phase-to-phase fault. And the issue there is around the 5 kV. I've had this issue with many customers. So the reason why 5 kV and 5,000 volts is such a delineation is because if you look at table 311.10c and 311.10c1 through C3, basically says that for a ground fault on your system that's less than 1 minute, you need 100% rated cable. For less than 1 hour, you need 133% rated insulation. And for a fault that's going to be on your system for greater than 1 hour, you need 173% rated cable. But if you look at the table, the delineation is not 5 kV, it's 5,001 volts. So for 5,001 volts and above, you have the 100, the 173, and the 133% rated cable. For anything less than 5,001 volts, there is no separation between 100, 133, and 173% rated insulation. I bring this up because we've had some customers who have come to us and they wanted a high resist. They wanted to convert a 600 volt system from a ungrounded system to a high resistance grounded system. They went to a cable manufacturer, and the cable manufacturer says they need to recable everything at 2 kV to compensate for the 173% rated insulation. It's not necessary. At 600 volts or low voltage, there is more insulation in the cable to protect the cable against mechanical stresses that it far exceeds the electrical rating. So medium voltage bus connected generators aren't designed to carry a great deal of single phase to ground fault current. In fact, you can probably generate more single phase to ground fault current if you have a single phase fault in a generator than the 3-phase bolted fault current, because there's such a low impedance. So you must have a low or high impedance grounded system. Typically, this is a low or high resistance grounded system. However, you can use reactors in this particular case as well. But what you want to do is you want to protect the generator specifically for single phase to ground faults. So why we use a low resistance grounded system, and the amount of current that you choose or the customer chooses for a low resistance grounded system has to do with how much capacitive charging current you have, for one thing. So if your capacitive charging current is over 10 amps or over 20 amps, then you need to go with the low resistance grounded system. A low resistance grounded system, you have to now look at your protection system. And if your protection system is going to be through conventional relays, then the ground pickup of conventional relays using residual current is going to be minimum, or the minimum value is going to be 20% of the let-through current of the capacitor, or sorry, of the CT. So if you have 2,005 amp CTs, your minimum pickup is going to be 400 amps. So this is why there's such a great difference between a high and a low resistance grounded system. So a low resistance grounded system, your minimum pickup of your protection system determines the level of ground fault current that you want to limit your fault to. So this is why there's always between 2 and 800 amps of ground fault current in a low resistance grounded system. All we need to do is overcome the capacitive charging current. If your capacitive charging current is 20 amps, the next step up is probably going to be 2 or 800 amps, or typically 400 amps, because the minimum pickup of your protection system is going to dictate how low an impedance you can use for a low impedance grounded system. You still want to limit the fault current to a low value. So this is the typical scheme we have for a low resistance grounded system and a medium voltage bus connected generator system. So when you have multiple sources and each one has a low resistance grounded system, you have damage at the point of the fault. In this particular case, if each resistor was limited to 400 amp 10 seconds, you're going to have 2,000 amps of fault current in that fault if all the generators are connected. That is a lot of current, and you're going to cause a lot of damage in your system, specifically if it's in the stator fault winding. You have shock hazard and stray currents, you have thermal and mechanical stresses, and transient overvoltages. The disadvantages: ground fault occurs within the stator fault winding. That generator is out for repair, and it's up for repair for a long time, and that's what happened in the Pacific Northwest. That the generator that had the damage was out for such a long time. It was basically a major rehaul. Now you have to buy more utility power to compensate for that generator not being there. And now you have demand charges that are on top of the damage that's already occurred. So if each generator is grounded through its own resistor, there are issues. So this is why the hybrid high resistance grounded system was developed. And this is the hybrid high resistance grounded system, so that each generator can have a ground return path of 400 amps in this particular case and 410 amps. So when there's a through fault, the maximum fault current is going to be 410 amps, but under differential conditions, if you have a stator fault winding, this breaker and this breaker open, allowing the generator to coast down with a 10 amp resistor, and it's going to limit the fault current. A variation of this is to use a zigzag on the bus. And I said to use a zigzag on the bus because it minimizes the fault current and is less complexity in the design. In this setup, you can add more generators and just put a 10 amp resistor on each generator. But in this design, there's more complexity in the contactor, differential protection. Well, mind you, you're going to have differential protection up there as well. But what we've done is we've taken that concept of a medium voltage bus connected generator, we applied it to low voltage. One of our customers in Canada came to us and said they have a system where they had 10 generators running, and you have 10 generators online, and if you have a 5 amp resistor on each generator, if you get a ground fault current, your current is going to be limited to 50 amps. Again, according to CSA and NEC, NFPA, if you limit the fault current to a low value in the NEC and to 10 amps at less than 5 kV in CSA, then you don't have to trip and you have an arc flash mitigation technique. If you limit the fault current to 50 amps, you must trip. So an alternative to this is to put a zigzag transformer on the bus and limit the fault current on each generator to a low value. In this particular case, we chose 0.5 amp. Same concept, because we just need to overcome the capacitive charging current up until this breaker. So we still protect the generator for single phase to ground faults before the generator breaker is closed and after it's open due to an internal fault. So a method of selecting resistor sizes. Obviously, you can use if the neutral is available, we have this particular scheme. You can use a transformer coupled with a resistor, or just use a straight resistor in it. And if that's the case, the resistor is equal to the line to neutral voltage divided by the fault current that you want to limit the fault to. So if you had a 13.8 kV system and you wanted to limit the fault current to 5 or 10 amps, you're limiting that's an 800 ohm resistor. Same thing with this particular scheme, and you can use this scheme or the resistor scheme, it doesn't matter. There's one advantage or slight advantage in that this particular scheme may take less room, but it's not really relevant in this particular case. What is important is that the codes have changed in recent years. So IEEE 32 has become C57.32, and CSA has developed a standard for neutral grounding resistors, and they both try to limit the amount of resistance change that you can have in the resistor during the 10-second rating, specifically for a 10-second rated resistor, because the resistor is allowed to go to 760 degrees C above ambient. When that happens, fundamentally, you change the value of resistance of the resistor, and if you change the value of the resistor, it's going to increase. And when it increases too much, you decrease the current and the fault current. So CSA says that you must limit the fault current to no more than, you can't have the current less than 80% of the let-through current, which basically means you can't increase the resistance by more than 25%. And C57.32 suggests that the resistance not increase by more than 67%. And there's an IEC standard that's being developed, which they've abandoned all resistance change because more or less it's just manufacturers in there. So there's 3 ways. I've been focusing on the zigzag transformer, but there's 2 other methods for limiting the fault current on the bus. You can use a Y-grounded delta configuration or Y-grounded open corner delta configuration. So the zigzag transformer is quite unique in that the winding of one phase is wrapped around one leg, and then the winding of another phase is wrapped around the other half in the opposite direction. So there's a net zero flux when you have no fault current. This means that you have a high impedance to normal system voltages. But when you have a ground fault, the zero sequence voltages have a very low impedance, and then you develop this neutral point, and that resistor over here limits the fault current. So if you limit the fault current to 400 amps, and at the fault, I've had this conversation with many people, at the point of the fault, your fault current is going to be equal to 400 amps plus the charging current. The charging current does not return back through the resistor. that charging current returns back through the capacitance of the unfaulted phases because they're connected to ground. Only through the resistor do you get the 400 amps. So you get 400 amps coming back through the resistor. So if it's a 13.8 kV system, you have 20 ohms. You have 133 amps returning on each phase because all three phases contribute to that fault. And you have a 960 kVA transformer if it was rated continuously. If it's rated for 10 seconds, you're allowed to derate that transformer, and the typical derating is about 3%. A Y-grounded delta transformer still have the same 20 ohm resistor over here. You still have the 400 amps, 10 seconds, and 133 amps per phase. Now you still have 960 kVA in that fault, and it can go to derate to 10 seconds. A Y-grounded open corner delta. This resistor over here limits the fault current, and you typically would not use this example for a low resistance grounded system, and I'll explain why. Typically you're going to have 40, okay, this is a 5 kV example, so 4200 to 120 volt transformers. When you have a fault, you're going to develop 205 volts across this resistor, and that resistor is going to limit the fault current. But the amount of current going through that resistor is going to be a function of 133 amps. So basically 4,666 amps is flowing through that resistor. So 205 divided by 4,666 is 0.044 ohms. Now you need a 1.6 MVA transformer to take care of that. So typically that particular example, this example is used for high resistance grounded system, because if you limit the fault current to 10 amps, now there's 3 1/3 amps flowing through each phase, 116 amps flowing there, and you just put a 1.7 amp resistor. So we've used this system for high resistance. And the other advantage is that you can put a pulsing contactor over here and change the value of the resistor and find where the fault is in medium voltage setups. And now you're switching at low voltage as opposed to medium voltage. And I know I've gone through that very quickly. Are there any questions? And here is the LinkedIn group, which Miriam said to earlier, and she will send out these slides to everyone who is listening.
Yes, Sergio. We will share a follow-up email in a couple of days, and we will share links to download a copy of the presentation, a webinar recording, the handouts that you can find at the right of the toolbar. So we will share all the resources that we have shared during the presentation. And let's move on to the questions that we got. Okay, the first one is, can you please talk about major challenges when grounding inverter-based generators?
Yeah, unfortunately, I don't know enough about inverter-based generators to discuss that right now, but let me do some reading on that, and I'll get back to you, because right now I don't want to discuss it because I really don't know too much about them.
Okay, thank you. The next one is, what application would you parallel a generator with the utility?
In what application?
Which application would you parallel a generator with the utility?
It happens all the time. If you look at pulp and paper facilities, and when you look at wastewater facilities, petrochemical facilities, they have enough energy that they produce a lot of steam, so they co-generate and offset the utility charges by generating their own power. So it happens all the time. I understand that at low voltage, you either have the standard utility and a standby generator in case you lose the utility. But there are many facilities that generate power, and this could happen for solar as well. Solar panels on the roof, people put those on the roof and generate their own power to offset the cost of the utility and minimize paying the utility any kind of charges. Now, what you need to work on is with your utility is whether you can export power or not. So you probably have to have a reverse power meter to take your utility off, or to take your generator offline if you start exporting more power than you're using. Utilities are good, but they love to sell you power.
Okay, excellent. Next question is, what is K in the formula you shared in previous slides?
K is a constant. What I can do is I can share the paper by Louis Powell, who developed those two formulas, because they're IEEE papers. I can send you references to those papers, and perhaps you can download them yourselves. I don't know if I'm allowed to actually distribute those papers. I can ask Louis, but K is a constant. Typically, it's about 1.5. It's not really I squared, it's I to the 1.5. So it's a value that's used to measure or determine heat produced by a fault. And you've heard power is I squared R, but there's a lot of losses and a lot of other damage, so it's about 1.5 works fairly well.
Thank you. The next one is, so under such a SLG internal fault cleared by a 87G relay, what could be the consequence of just having a neutral side breaker and open it to clear the fault completely internally?
Yes, you can do that, but then let me go back and I'll show you what that's going to look like. All right, so you basically don't have this. Oh, sorry. And you don't have this. So you want to open up this breaker and remove the generator breaker, or the neutral grounding return path for the generator when the differential picks up. The danger in this is now you're coasting down when you have a stator fault winding fault in an ungrounded system, because there's no ground return path, and this could be just as dangerous, in fact more dangerous than having the 400 amp resistor there, because think about it, when you have an intermittent arcing fault, and you're going to have an intermittent arcing fault specifically in the stator fault winding when you have a ground fault in the stator fault in stator. So your generator is now ungrounded, and you can have catastrophic damages in an ungrounded system during an intermittent arcing fault, and you're going to have over voltages on the system of 6 to 8 times the normal system voltage. And there's been documentation of how that has been more catastrophic than leaving the 400 amp resistor there. So again, this is one of the things that IEEE looked at in this special group to determine what the possible solutions could be, and having the generator ungrounded was far more dangerous than, not dangerous people-wise, but dangerous equipment-wise than having a 400 amp resistor there. I hope that answered your question.
Thank you. Let's go to the next one. Is how did you size the neutral wire?
That's a good question. There is a formula in NEC that, because you really don't need, the cable doesn't need to be sized to carry 400 amps continuously. If it's a continuously rated resistor, then yes, you have to have a continuously rated wire. If it's a 10-second resistor, there is a formula in NEC and in IEEE 3003.1 which allows you to decrease the size of that wire, but you have to ensure that the current flowing through that wire does not extend beyond the temperature rating of that wire. I can see if I can find the reference and I'll send it out to you. But yes, you can simply use a in low resistance or medium or high resistance grounding systems. CSA allows a 14 gauge wire to be used for a 10 amp resistor. NEC states that you have to use a minimum number 6 copper or number 8 aluminum wire for a high resistance grounding system, but there's no help in low resistance grounding system. So I will send you that formula that you can use for that. Marian?
Sorry, Sergio. Yes, let's go to the next question. How did you account for failure of switching device, between brackets, contactor, on generator LRG resistor?
Well, proper maintenance. You'll always have to exercise these contactors and make sure that they're functional. Everything is going to depend on maintenance. Even if these are reputable devices that we put in, and they require maintenance or exercising, at least much like you would have to exercise the breakers. So nothing is going to be a substitute for maintenance and ensure that everything works when it's supposed to work. On the same token, you have to calibrate all your 87 relays and make sure that they're functional. Maintenance is paramount to almost everything else.
Excellent. We have been getting a lot of questions. So far, we have 16 questions. So for sure, we will need to develop a Q&A document.
Well, we always develop the Q&A document. That's how I get all the salespeople to actually do anything for me.
Okay, excellent. Next question. Do you have any guidelines for sizing a bus Zig Zag resistor, say 200 amps versus 400 amps? Are there any high-level estimation methods to size these based on the system?
Again, the low resistance ground system is going to be sized so that the minimum ground fault pickup selects the size of the ground fault resistor and the zigzag. I have no preference. There's no real cost differential between a 200 amp or a 400 amp 10-second resistor. Little bit of a size difference, but there isn't that much of a cost differential. So what determines a 200 amp versus a 400 amp is whether you can detect a 200 amp ground fault. And this comes into play with, I can give you an example, which is very simple. If you have fuse protection downstream and your largest fuse is 390 amps, you're not going to pick a 200 amp resistor and a 200 amp zigzag, because it might not be enough with the load that you have on the system operate that fuse and clear the fault. And the danger in not clearing the fault is overheating the resistor to such a point where it becomes an open circuit and you'll never have a fault again.
Thank you, Sergio. So the next one is, does I-Gard offer engineering services to assist with preparing calculations and sizing equipment for hybrid grounding of generators?
Yes, that was the easiest question to answer.
Okay.
What we need to do though is we need to, if you give us a single line diagram and a cable schedule, we can probably determine what the capacitive charging current is of your system, and then look at your protection scheme and see what the minimum pickup is for ground faults, and then size everything accordingly. And unfortunately, we need to know the method of operation. Again, we went back to this scheme. Are you always going to have the utility on? Are you going to have the utility cogen? Are you going to be islanding? There's a lot of questions involved, and we have the questions. You have the answers. We can get together and come up with a solution.
Next question is it possible to have resonance with an NGT and the capacitive reactance of the cables during a fault?
I guess it would be possible, but it's highly unlikely because you have a lot of resistance in there too, which dampens the effect of the resonance. So I guess it can be possible, but are you asking for a transient or okay, let me go a step further. If there is transients available, we have surge protectors that you can put over here across the resistor that will limit those overvoltages that are caused by the transients. There have been some studies that are done on that. That was the 5th paper on hybrid high resistance grounding systems. And what I'll do is, so make a note, please, Miriam. I'm going to send out the Louis Powell reference paper and the 5 papers for the hybrid high resistance grounding system.
Okay. Okay, perfect. So next question. Do you need to monitor the HRG on the generator or just the LRG on the grounding transformer?
That's a great question. I'd say you have, well, I think in Canada you have to monitor the integrity of a resistor per code. So I think you have to monitor both, but one can make the argument that it's the low resistance grounding system which is the main grounding scheme. So unfortunately, it's going to be under the jurisdiction of the authority having jurisdiction to determine which one is going to be monitored. But typically they're going to default to both because I think in Canada it's a new requirement to monitor the integrity of the resistor or what to do when something happens to the resistor. And I think right now they're going to push it as far as they can. But I think it's also a good idea to monitor both.
Okay, thank you. Next question. Would the same hybrid system apply if you are a generating station that exports to the utility?
Would hybrid grounding, if you
are a generating station that exports to the utility?
Well, it depends. If you're a generating station, are you generating at medium voltage, or are you generating at low voltage and stepping up to transport to the utility? So there's a couple of things that you have to look at. If you're connected directly with medium voltage, then yes, you want to protect your generator. And the typical fault that you're going to have on the generator, and what you need to protect it against, is a medium volt or a stator fault winding. So you want to minimize the damage should you have a stator fault winding. So it's in your best interest to put in a hybrid high resistance grounded system. If, however, you have a unit connected generator and you have a transformer isolating the generator from the utility, then you could probably get by with a high resistance grounded system and minimize the fault current that way. You could still isolate if you want to, depending on whether you're generating at 5 kV, 4160 volt, or 13.8 kV or some other medium voltage distribution. So there's, I would need to know more parameters, but basically these are the things that you need to ask yourself. If you're going to generate and export power, you're selling power. You want to protect your asset, because if you're not generating power, you're not generating income. And that's the sole source of your business. So you want to protect your business, and it's like an insurance for your business. You want to put in that hybrid high resistance grounded system if you're connected directly with medium voltage. You also want to put in a high resistance grounded system if you're connected with a step-up transformer.
Perfect, thank you. I believe we still have a couple of minutes for an additional question. Can you talk about the design of Zig Zag transformers for a split bus tiebreaker system?
Well, if the tie is open, each half of the system will be its own source. If, however, the tie is closed, those two zigzag transformers and resistors will be in parallel. So if you want to limit the fault current to, if it's low voltage, what we've done is we put 5 amps on each side, so that when the tie is closed, your fault current is limited to 10 amps, still within the boundaries of CSA and Z462 and NFPA 70 and NFPA 70E, in that you have an arc flash mitigation technique and you limit the fault current to less than 10 amps. And I'm taking liberties here, hoping that it's a low voltage or less than 5 kV system. So again, you have to look at the topology of the system and determine what you can live with and what you can't. And again, if you email me with the particulars, any of these questions, if you email me with the particulars, because I've taken liberties with some of these questions and made a lot of assumptions. If you send an email to support@i-gard.com with the particulars, we could have a better answer.
Excellent. Let's go to the last question. What switching considerations does the contactor in a hybrid system need to take into account? Is there a potential for transient switching voltages?
Oh, I'm sorry. Can you read that again?
Yes. What switching considerations does the contactor in a hybrid system need to take into account? Is there a potential for transient switching voltages?
There is a potential for transient switching voltages, and then what happens is we put in transient voltage surge suppressors, or was it zinc oxide lightning arrestors to limit the potential rise. And we have a source of those particular devices that can be used for three-phase transient overvoltages, as well as single phase, and you only need a single phase to protect the neutral. So we have a source for those as well. And again, the fifth paper in the sequence of the medium voltage bus connected generators addresses that.
Excellent. So since we got several questions from the attendees, we will work on a dedicated Q&A document, and we will post it in our website for everybody to read it. So thanks for your questions. That brings us to the end of the Q&A session and to the webinar itself. Thank you, Sergio, for your presentation today, and thank you to all the attendees. In a couple of days, you will receive a follow-up email, including all the links to the different resources we shared during the presentation. We encourage our customers and potential customers to follow I-Gard on LinkedIn. We also have a LinkedIn group, as Sergio mentioned earlier. It is named Grounding, Earthing, Bonding, and Ground Fault Protection. Thank you again. We are looking forward to see you attending our webinars in 2022. I don't know, Sergio, if you would like to add anything else?
No, again, I've made a lot of assumptions in these questions. If you want more specific answers to your question, and if I took too many liberties with your questions, please email support@i-gard.com, and we'll be happy to address your concerns.
Thank you. Have a good evening, all of you, and stay safe.
Sorry.
Yes,
Miriam, there is going to be a PDH that's going to be sent out with this. Is that correct? Or I think one of the questions, the last question was, is there going to be an attendance certification?
Yes, we can create a PDH certification. So just let me get the attendees list, and I will reach out to you to get more information and see next steps.
Oh, and just in case I forget, have a safe and happy Christmas to our American friends. Happy Thanksgiving coming up, and please stay safe.